welcome to the new episode of the series Building an Autonomous World from Scratch. In this episode, we will be developing the motor controller for our robot. The main purpose of the motor controller will be to control both motors, the left one and the right one, to then achieve the desired velocity in terms of linear velocity and angular velocity. On the last episode, we have developed the motor driver, and then this motor controller will be using two motor driver instances, one for the right and one for the left. Since the previous episode, I have fixed one bug, which was regarding the PID controller. I forgot to set the here, if you can see here, I forgot to set the PID output limit, so there was no negative values in the correction. That is now fixed, and I have also improved the PID constants for the motors. Lastly, I've also created a documentation using Doxygen, right? So you can basically, if you want to run it for yourself, you can go to the Doxygen slash Doxygen generator slash HTML and then run a Python server like this. Then you can go to your browser and type localhost colon 8080, and you will be seeing this right here. Now if you click, now eventually I will put here some information, but for now you can go to the classes list and you can see all the different classes we have so far. So for example, the motor driver, you have all the different methods available with their explanation, of course. Now, regarding this, well, now we can go then to the motor controller implementation. So as usual, we will start with the header file. So if not defined, motor controller HPP. Okay, and now before, well, we can actually do the class motor controller for now. Okay, but before we develop or create the class itself, we also need to define, of course, thank you Copilot, we need two different structures. Now our motor controller will be when receiving inputs, as in command velocity commands, which are used in ROS, and it will also output the pose of the robot, or also known as the odometry. And so let me also include in the Arduino. We will need then a command velocity structure, and this command velocity in ROS we have linear velocity and angular velocity. So each one of those has x, y, z parameters. But in our case, since our robot can only move forward or backwards and rotate along the z-axis, we will only have essentially two values, so the x value and the angular velocity value along the z-axis. Then we also need a form of storing the pose of our robot. And to make it easier, we will also create a structure which will have then the value x, y, and then the orientation. So to do this, we define a struct, and we will call it CMD velocity. And then this here will have float x and a float w, which stands for the angular velocity. Right, then we will define the struct for the pose, right? And this will have float x, float y, and then float theta. Okay. So with these two structures done, we can now move on to the class creation, right? The creation of class, sorry. So we will have a constructor, motor controller, and what this motor controller will take will be the two motors, so left and right, and and the distance between the two wheels, right, between the two axes basically. So we will take, first of all, we need to include a motor driver, the one we have done in the previous video. So we will need a motor driver, left motor, and a motor driver. Okay, that's pretty much this here without the wheel radius. Now we will make this a pointer. Okay. Then we need a void set command velocity. It already knows. Void get pose, and then we will pass it like this. We need a void run, and we will need also a void print pose, right? And lastly, we need a void reset, which will reset essentially the pose. Okay. Now we need two private methods. We need a void compute wheel velocities, and a void compute pose, exactly. Okay. Finally, we need some attributes, which will be then the left motor, the right motor, and the distance between the wheels. All right. And we actually need one more, which is a timer, which is also something we implemented in the last episode. No, timer. Okay, timer. Well, not timer, but let's call it motor update timer. And also let's add here _, to mention this is private. Okay, so this is all we need, and essentially only these two methods here are the important ones. So I will go and I will fill in the boilerplate code such as the setters, run, and so on, and I will be right back. Okay guys, so I'm back here, and I've said I have filled in the boilerplate code. So I've initialized the constructor and initialized the variables. And there's an additional thing here is the motor run frequency, which I have added to the configuration. And this is basically how fast we should run the run methods of the motor driver. And I've set it to 20 Hertz. And also that's why I have 1000 divided by this to get the milliseconds out of it. Then the set command velocity, we just set. Oh yeah, also I forgot this. Forgot to include the pose and command velocity as attributes as well. So in this case, I just set command velocity to the command velocity and the pose to the pose. The reset just calls the reset from the motor driver, and this is something I have implemented as well. Well, after the last episode, and it resets the pose and the command velocity, and now. Well, actually the print pose as well, it's just printing the 3 variables. And then these are the methods left. So the run method is pretty straightforward. So we just first check the motor update timer, if it has elapsed. If it has elapsed, then we first compute the wheel velocities, we compute the pose, and we tell the motor, the left motor and the right motor to run. Okay, that's basically it. Now, before we move to these two methods here, I would like to show you first so how to actually compute the wheel velocities and to compute the pose. I have written here some guide, and I have taken this from a YouTube video I saw. I will try to find it and link it here and the left or right, I don't know, and also in the link description, in the video description, sorry. So yeah, if you want more details about this, you should then go see the video. So what do you have here? So first of all, we have some acronyms. So we have R, which is the wheel radius, L, which is the distance between the wheels, and theta, which is the angle of rotation. And here we have our robot in its world, and it's currently at position Y and position X. So yeah, the distance between the wheels is this L, and then we have the radius, and the angle of rotation is relative to the X and Y axis. Now, essentially, the way we compute the both the pose and the wheel velocity is based on a kinematic model, and then this model is defined as follows: we have an x, which is r over 2 times the velocity of the right wheel plus the velocity of the left wheel times the cosinus of theta, and then for the y we just do with the sinus of theta. And to get the orientation, well, just the radius over L times VR minus VL. Now, there's some problem with this. Well, we actually are using the velocity from the right wheel and the left wheel, but we actually want to know what should be the velocity based on some linear and angular velocity. And so that's where the unicycle model comes in. The unicycle model is defined as follows. Well, x is the linear velocity times the cosinus of theta, the y is the linear velocity times the sinus of theta, and the orientation is just the angular velocity. Now, this still does not give us how to compute the VR and VL, but what we can now actually say that this x is the same as this x, and so we have the following equations. And if you try to solve this for both VR and VL, you will reach eventually these two. Okay? And here we say, well, VR is actually 2 times the linear velocity plus the angular velocity times the distance between the wheel divided by 2r. And then I have added here a scale factor. The reason I have this scale factor here is because since our motor driver, it has only a velocity, a maximum velocity of 0.6 meters per second, if you, for example, send a 0.5 meters per second velocity, the value you would get here would be a 14 point something. And so what I've done is just take this 14 point something, and I divided by the actual velocity we should be getting, which got me some scale factor basically. And then I just multiply this so that we have a velocity which is from, let's say, 0 to 0.6. But yeah, so this is the important part. So these are the two equations, or this is basically the equation we want. Now, to get the robot pose, first thing we need to do is actually get the right and left wheel distances. That is coming from our driver. And for the pose itself, we need to know what is the actual distance from within the center of the robot. So this one here on the showing in green. And well, this is pretty straightforward. You just add both the left and the right distances and you divide by 2, and then you get this dc. And then to compute the pose, well, the x axis, so the x value, will be the initial pose, which in our case will be always 0, plus this dc times the cosinus of theta. The y is the same, basically, so the initial position, which is 0, plus this dc times the sinus. And the theta, well, is the initial theta, which is also 0, plus the a distance of the right wheel minus the distance of the left wheel over the distance between each wheel, well, the both wheels. And so, but that's basically all we need. And this is what we need to implement in our code, this and this right here. Okay, so how can we do this? So let's start with the wheel velocities. So the wheel velocities, we can get the distances with the following. So first of all, we will compute VL, which is equal. And before doing this, we will actually need, let me go back to the formula here. We need the command velocity times the angular velocity times this over this, right? Okay, so this, so it's 2 times command velocity dot x, right? Plus the CMD velocity dot w. Why don't I have times the wheel distance between wheels, and here it's 2 times the wheel radius, and the wheel radius we get it by having left motor dot get wheel radius. So what is wrong with this? Oh, it's missing the times here. Okay, now we do the same for the right wheel, and so it's still the same, but instead of being a plus here, we have a minus, and yeah, that's it, right? So plus and minus, that's the only thing that changes, and we need this scale factor. Now this scale factor, we will apply it here, which is, so it's the VL in this case, times 0.0338. I guess this basically is the wheel radius, sorry. And same for the right wheel, and then we just say that the left motor we set the velocity VL and the right motor the velocity R, and that's basically it. Now for the pose, we will need first of all the motor data, left motor data, and then right motor data, and then we need to get the left motor data, the right motor data first. Okay, now we compute DC, which is then equal the right and the left divided by 2, and then the pose X is equal, in this case 0, so we don't need to add it. So it's DC times that, dy, it's a sinus, and then the theta is this. So if the distance divided by the distance between the wheels, just checking if it's all correct. Yes. Okay, that's pretty much it. Now you can test this, and to test this we will change this main file. Okay, so I will copy paste what I have here. So what do I have here? So first of all, I create 2 encoders, one for each wheel, and then 2 motor instances, right? I then create the motor controller where I pass the left, right, and the distance between wheels, which is again in the configuration file right here. Then I have two functions for the encoder's interrupt service routines. And I created here a function setup interrupts, just an helper function really. Then I have here a command velocity value just to see if the motors are actually turning. Okay, then so I set up the interrupts and I send the command velocity to the motor controller, which then the motor controller should send to the motor drivers. And then I just simply run the motor controller and I am printing here the pose. So we can test this. So prun run first. So here is the short clip, and yeah, you can see the robot rotating at constant velocity in a circle manner, and that's it. So hope you have enjoyed it. Okay guys, so that was it. This was the motor controller. So in the next episode we will be then developing the last part of our low-level development, which will be the serial protocol. And with that part we will have everything we need from our low-level part. And from there on we will be working with ROS mainly and making it autonomous, right? If you have enjoyed this video, subscribe, comment if you have any questions, and see you on the next episode.